All right, let's take a look at this particular optimization problem from Khan Academy. Now, you might have seen questions along these lines where it's something like, try to minimize the amount of fencing necessary to pasture in 32 square yards or something like that. And for me, that intuition came into my own sense of how to solve this. But let me go ahead and show you a little bit of my failures before I actually go through and solve this the right way with you. So here's what I was looking at the other day, and I figured, okay, this should be pretty easy. And I threw myself at it, and it just didn't jump out. Which sometimes happens, right? So I said, hey, maybe, 32, that looks like a power of 2. Maybe there's something special there. That didn't work. I started to set up my basic equation and just kind of threw myself into it and got this funny radical here, a cube root of 32, which I didn't like. So I thought, hey, maybe I'll actually be able to simplify this by using Lagrangian optimization. Let's use something that you guys haven't seen yet, but we have a problem where we're trying to optimize with a constraint. So I started doing this math over here, and again, it just didn't pop out for me. So first I thought, well, maybe I try and deal with this in the grade book, make this extra credit or something like that. And I thought, no, it can't be that hard. So one thing that really helps with problem solving is you attempt the problem, you put in some time, you fail, then you walk away. Right? This is why showers have this reputation for being a place where good ideas happen. You have a flash of genius in the shower or taking a walk or whatever. It's not that the shower is special or that taking a walk is special. It's that the process of loading a problem into your brain and then walking away can be incredibly helpful. Somewhere, oh, here it is. A book that really helped me thinking about these sorts of problems is Pragmatic Thinking and Learning by Andy Hunt. It's a really excellent book that I read, I think must have been in either undergrad or grad school about a decade ago. And he goes into some of the psychology, some of the neuroscience, but he's kind of giving you, oh wow, when was this? 2013, that is an old plane ticket. He goes into this general question of how do you get better at using your brain? Now, their target audience, or his target audience, is computer programmers, but it is equally applicable to economists or anyone. All right, all that said, let's jump back into this. So this morning I took another swing at this and it just popped right into place. And I think the reason that was is because I had already loaded it into my brain. So when I took another attempt, this third attempt, this is when things finally clicked. So let's set up our problem. We want to minimize our surface area. We're going to have this constraint. So subject to, we're going to see this sort of notation more when we get to constrained optimization. Volume is going to be 32 cubic feet. And our surface area, well, I'm going to lay out some terms here. So we've got this aquarium. And I'm going to avoid the very real problem of making sure that, say, there's enough that we can sort of have some splashing. Let's not worry too much about that possibility. So we're going to think about this in terms of, let's say, depth. In this dimension, we'll call this height, and we'll call this the width. What symbols we use, not super important, but we've got these symbols. And I'm going to go back to that intuition of fences. You might have seen problems like this. So it's something like fence in, so a two-dimensional version, fence in, let's say, 32 square feet, or I don't know, square meters or something like that, and minimize the perimeter. Right? So we've basically got a very similar problem here, except instead of minimizing the perimeter, if you remember these questions, I think I had these questions as far back as middle school, the basic answer you got was the width times the depth. The way to minimize your use of fencing was to make it a square, right? So depth equals the width. So I'm going to use that intuition in a minute. Now another thing I'm going to do, so actually let me start back here. Let's set up our objective function. So the surface area, what is it going to be? I'm going to assume that we don't have a top on this aquarium. So I've got one side, 2, 3, 4, 5. 4 of those sides are the outsides, 1 is the bottom. So the bottom is going to be depth times width, and then I'm going to have 2, the front and the back, which are going to be width times height, and then I'm going to have 2 on the sides that are going to be depth times height. All right, now V, our volume is 32, and that is going to be depth times height times width. So I'm going to start by rearranging this. I'm going to say height equals 32 divided by depth times width. So this way I'm going to get rid of one of the variables, and hopefully that'll make life a little bit easier. So now my surface area is going to be, let's see, I've still got depth and width. I'm going to come to this square intuition in a little bit, but let's just lay it out explicitly. So depth times width, we're going to substitute height in both of these cases. So we're going to have 2 times width times 32 over depth times width, plus 2 times depth times 32 over depth times width. So we've taken our setup. Well, first we set it up, right? The big thing here is setting up the problem. We set up the problem. We used our constraint to say, well, if we've got to have 32 cubic feet, then it must be the case that the height has to have this value, right? So that means that we can reduce the amount of variables in here. So now we've gotten rid of all of our h's. So let's start by simplifying a little bit. So we can get rid of width and width. We can get rid of depth and depth. And now we've got depth times width plus 64 over d plus 64 over w. So we're going to be trying to minimize this, but now let's just kind of think through this a little bit. Let's imagine we had a smaller depth but a longer width, and let's just keep height the same. Right? Let's ignore the fact that this is going to be a little bit different. Although actually that intuition might help us in just a second. If we think about what's going on with the surface area, well, we know that we're going to be expanding the perimeter of the base. Well, what does that mean? That means if the height is fixed, we're going to be using more glass for these, back to the front and the back side. We're going to be using less glass on the sides, but because the perimeter overall is getting bigger, it must be the case that we're using more glass. Now, if we think about here, the height is also, of course, going to be affecting our glass. So I'm just kind of doing not rigorous math, just really back of the envelope math to kind of check my intuition. And then I'm just going to throw it at the wall and see if it works. Spoiler alert, it does. So in terms of height, we're thinking 32 over something. Let's see, what does that mean? So 32 over something, well, depth times width, if we make depth much bigger, the width bigger and the depth smaller, what's that going to result in? Well, let's kind of think of if we had something like, now, you know what, it's back to the envelope stuff. Let me not get caught up in that. Let me jump back to here. So, surface area, I've got a function, and I'm going to use this intuition. to make D and W the same. Right? So I'm just going to say depth equals width, and I'm going to rename this. I'm just going to call it X. So now our equation is x squared plus 64 over x plus another 64 over x. Well, that's just 128 over x. Or, this is going to be a little bit easier for me. Your mileage may vary. This will be plus 128 times x to the minus 1. Now, we've got our setup. Let's find our first derivative. This is going to be 2x plus the derivative of this. Well, we got a minus, so actually this is going to be minus 128 times x to this power minus 1. Minus 1 minus 1 is minus 2. So now we've got our first derivative, and we can set this equal to 0. All right, so what do we do with this? Well, we've got 2x. This we can move over, so we can say 2x equals, what's this going to be? This is 128 over x squared. Well, we can multiply both sides by x squared, and that's going to give us 2 times x to the 3 is equal to 128, which means x cubed equals 64. And hey, that intuition I had before about a power of 2, this is going to come back and help me. So x cubed, let me just double check here, right? So if we've got 64, that's, 64, that is 8 squared. All right, so x definitely has to be smaller than 8. 2 cubed, 2 times 2 times 2, well, that's going to be 8, somewhere between 2 and 8. But actually, it's going to be pretty easy, a nice round number in this case. It's going to turn out that x is 4. Right, so 4 times 4 times 4 is 16 times 4. 16 times 4, that's going to be 40 plus 24, which, hey, is 64, which means we've got x equals 4, solves this equation. All right, so our base and our height, our base, our width and our depth are both equal to 4. We're assuming a square aquarium. So let's go ahead and see what we get when we plug this back into here. So h equals 32 over depth times width, which are both equal to 4, so that's 4 squared, which is 32 over 16, which is 2. So we don't have a perfect cube, right? But we have something that is 2 feet tall and 4 feet in either direction, in the depth and the width. I guess height might make a better term for depth in this case, but 2 feet high, 4, 4, and that should give us our equation. So let's go ahead and plug these back in. All right, so this is our depth and our width. This is our height. If we go back to our surface area, we could do this version, but let's just plug it back into the original just to make sure this all makes sense. And we'll check, change colors just to make it a little bit easier. Depth times width, that's 4 times 4, so surface area is going to be, right, this is the area of our bottom sheet of glass. That bottom sheet of glass is 16 square feet, right? 4 feet times 4 feet is 4 square feet, plus 2 times W times H, which is 2 times 4 times 2. Well, hey, check that out. That's another 16. Is it 16? Whatever. I'm pretty sure it's 16. It's early. 2 times 4 is 8, times 2 is 16. And then, hey, we're going to have the same thing here. Since the depth is equal to the width, the height isn't changing within the equation. So 16 plus 16 plus 16, which is going to give us 48 as our surface area. And when I plug that into Khan Academy, it says, hey, we've got the right answer. right? 48 square feet worked for that. All right, so let's take a quick look at what we did. So first, in metacognition terms, we did a couple things. One is, or I did a couple things, I loaded this into my brain by going through, by making an attempt, and even though my attempt failed, it was still valuable. This was still a part of me solving the problem. Even though I didn't use any of this math, I guess I did use that, but even though I didn't really use this, it was a part of the process. Another metacognitive thing is I tied this back to something that I remembered from a long time ago in some math class where I almost certainly asked, when am I ever going to use this? And the answer was to solve a similar problem, which in this case, I don't know, when am I ever going to use the question of minimizing surface area for building an open-topped glass aquarium? I don't know. At the very least, it's good for my brain, right? I feel pretty good having done this, even if I'm not going to go down to my local fish store and help them save money on glass while they build aquariums. All right, so that's the metacognitive stuff. The actual solution. So most important was setting up this equation here, which gave us an objective function. I also used this constraint to simplify the problem a little bit, right? So if I didn't have to hold in 32 cubic feet, then, well, things would be different. But given this problem, I was able to use that. I know that this equation must be the case, which means that I can put h in terms of d and w, and I can get rid of those h's, right? That makes the problem a little bit easier to solve. Applying this intuition to this made it even simpler, means instead of dealing with two variables, I was able to deal with just one variable. And given that, I was able to set it up into a simple equation where I could apply a derivative, check to see where it's zero, and solve. Now, I didn't check the second order condition, so let's really quickly look at that. So given x equals 4, what is our second derivative here? Let's just squeeze that in here. That's double prime. This is going to be 2. Minus 128 times something. We're going to have that minus sign, so we're going to have another positive something, right? So positive whatever's going on there. Okay. Something greater than 0. I'm not even going to bother figuring it out. 2 times this, but most importantly, negative and a negative. X is going to be a positive because we can't have a negative width on our aquarium. So our second derivative is positive, which means as we're varying x, our surface area looks something like this, and we're finding that minimum at x equals 4. Right? It could have been the case that we had a negative second derivative, in which case we would have been maximizing. Great, so we solve for x, we use that information, we solve for h based on this constraint, we plug it all in, and it worked. All right, as always, if you've got any questions, feel free to ask in the usual places.